Hi, going to deal with separating techniques within the GCSE syllabus. So the obvious thing would be if you've got chemicals mixed up, you've got a mixture, how do you separate them? You could use common sense, like you've got green marbles and red marbles, you just pick out the green marbles from the red marbles. The chemicals are a bit more complex. We need to use the differences in the properties of the chemicals that are within the mixture, and we'll do those and we'll use those differences to separate them. And obviously there's no one technique. There are lots of different techniques, and you use whichever one you think is best. And sometimes you can use a mixture or a combination to achieve the separation. Anyway, let's get going. So the choice of what technique to use will depend upon the physical properties like boiling points, whether it dissolves, its diffusion rate, those kind of things. And we're not in this section going to use chemical properties. Now, chemical properties are reactions. So how these things react, that's for later. That's like when we get on to A-level chemistry, we will use the reactions to separate them. And then after they've reacted, we'll react them to go back to what we originally had in order to separate them. So we're going to deal with physical techniques, using physical properties, and there are a few of these that you need to know about. So the first one, let's talk about what this word means: miscible and immiscible liquids. The word miscible means liquids that mix together. Famous example of miscible is alcohol and water. Alcohol and water in any proportion will mix together perfectly well. 90% alcohol, 10% water. 10% water, 90% alcohol. Sorry, I've just said that. Let's go the other way around. 90% water, 10% alcohol. The proportions don't matter. Alcohol and water are miscible. Now, the opposite of that is immiscible. Look, immiscible. Now, immiscible means they don't mix together. So when you put them in the same vessel, you get layers. Now, the most famous example of that is oil and water. And when you put oil and water together and you let it settle, the oil will settle on top of the water. That's because the density of oil is less than 1 gram per centimeter cubed, which is what the density of water is. The lower density liquids always float on top of the bigger density liquids. And so water is the bottom layer and oil is the top layer. So what if we've got such a mixture like oil and water, or some other mixture where the two liquids are immiscible? How do we separate them? Well, this is the simplest kind of separation technique that we have at our disposal, and really it just involves using one piece of apparatus called a separating funnel. Now, that's a separating funnel. I will show you in the next video where I actually do this physically as a practical. All of these techniques I'm going to show in the next video, but the separating funnel is the simplest. Look, you put your 2, or sometimes there are even more than 2 liquids that are immiscible into the funnel, and you close the stop tap. So the stop tap is closed. When they're in there, because of different densities, then the lower density liquid will float on top and the higher density liquid will be underneath. Now, if you put a beaker underneath to collect whatever it is we're going to collect, then you use it like this. Now, specifically, I'm going to use the example of water and oil because that's the example they use most. I can't remember in my many years of teaching them in exams using anything different. So if you had oil and water, you would open the stock tap, open it, let the water there run out. You can see the layer. You can see the layer reducing. You can see the oil layer getting closer to the stop tap. You can stop it almost exactly down to the last couple of drops. Accuracy. You can stop the flow of the liquids out of the separating funnel until the water has left and the oil is still in there. So within a few drops you get that really well position, because you can see, this is normally glass, you can see where the two layers are coming through, and you stop it when the water's gone and the oil is still in there. Then you change the beaker. So get a different beaker, you've collected the water, change the beaker, fresh clean beaker, and open the stop tap again. And now you let the remaining liquid, the oil, you let that out into a second beaker. So you'll have your two beakers, one with water and the next one you've collected with oil. And that is a way of separating oil from water, or separating any two immiscible liquids, or separating immiscible liquids in general. That's a very simple idea. Hope you understand that, and I'll show you next lesson. Right, it's harder when we get into solutions. Now let's understand the terminology and what makes up and constitutes a solution. So nearly always the solvent at GCSE is water, and we've dissolved something into it. Whatever dissolves into the water is the solute, and the water we call the solvent. And together the solvent and solute make a solution. Now that solution we're going to use a lot throughout chemistry, and it's always, I want you to have the mental image. I want you to have the image that something, solute, is dissolved inside something else, solvent. So here the example is sugar. Sugar is the solute, water is the solvent. Sugar goes into the water, makes sugary water. That sugary water is a solution of sugar. So, solution, sugar is dissolved in water, the sugar dissolving in the water. Now, that's just one example. We could talk about salt dissolving in water, make salty water, copper sulfate dissolving in water, making copper sulfate solution. Any solution, I want you to mentally know that there's two components. One is the solvent, that's the stuff doing the dissolving. The other is the solute, the stuff that's dissolved. Now, because solutions are so very common, then we have to separate them. Sometimes you want the solute and sometimes you want the solvent, and you need different techniques if you want the dissolved things in the solution, or if you want the solvent, the stuff that's done the dissolving. And let's have a look at the simplest one first, which is, say you got salty water and you want salt, or sugary water and you want sugar, or copper sulfate solution and you want copper sulfate. Then what do? Well, this would be a simple case if you had the solvent water. How about boiling off the water? Idea. Let's have a look. So, to separate the dissolved solute from the solvent water, then just boil away the water. If you boil away the water, you'll be left with crystals of whatever was dissolved. So if you had salty water, you'll be left with crystals of salt. Sugary water, crystals of sugar. Copper sulfate solution, crystals of copper sulfate. Finally, we'll be left with the crystals if the water boils away. But I'd like to introduce crystal size into this, because occasionally that comes up. If you boil away the water quickly, the crystals form quickly, and then the size of the crystals is tiny. So the faster the crystals form, the smaller is the crystal size. If you make the crystal slowly, then the crystals will grow, and as they grow over time, they end up being bigger. And often we need in exams a method. They'll say, how do we make good large crystals? And for that, you need to do it slowly. So if we're making crystals quickly, we boil off the water today. If we want to make the crystal slowly, boil off some of the water today and leave the crystals that are starting to form, leave them for the water that's remaining, leave that water to evaporate away of its own accord over days, and then the crystals over that period of days get bigger and bigger and bigger and bigger and bigger and bigger, and we end up with much bigger crystals that way. Now, just bear that in mind. So, what apparatus do we use? Well, you're familiar with a Bunsen burner, tripod gauze, evaporating basin. You put your solution in there. When you boil off the water, can you see the water boiling off from the top there? The particles of the water are leaving that evaporating basin. They're leaving it, they're going up, mixing with the air. But crucially, the solute is not. Crucially, the solute is staying there. So, salt and water, the water's leaving, the salt will form crystals. Now, I've tried to label with my own handwriting here, crystals of salt. Those are the little specks that are there. The crystals start forming, and they are the crystals of the solute, the stuff that's dissolved. Now, unsurprisingly, this technique is called crystallization. So if you want the solute, and the solute's dissolved, and you boil off the water, it's called crystallization. If you want good big crystals, boil off some of the water, leave the remaining water to evaporate away slowly, and then the crystals will be bigger in size. So, what about if you've got a solution and you want the solvent? Now that's harder. We can't just boil it away like salty water. What if you want the water? Sugary water, you want the water. Copper sulfate solution, you want the water. If you want the water, you can't just boil it away into the air and let it mix, because then how do you get it back again? If you want the water, then you fundamentally have to have a different technique. And we are going to boil it. We are going to let the water boil off from the solution. And when it does so, it's going to boil off as steam. The key now is to collect that steam. How do we collect the steam, and how do we cool it back down into the water that it clearly will be if we cool it down to below 100 degrees? Now, that's called condensation. Whenever we've got a gas, like steam, you cool it down, and you reform the liquid, it's condensation. So we are going to condense the steam. The steam will be condensed, and we're going to turn it back into water. How are we going to do it? Well, I'm going to introduce you to a piece of apparatus which hopefully you've come across in general science. It's called a Liebig condenser, or more generally in science, it's called a condenser. I think the older teachers like myself, we learned it was a Liebig condenser. It was Mr. Liebig that designed the apparatus and the Liebig condenser. But nowadays, when I look on exam papers, it's labelled condenser. This is it. Now, I once took one of these that was broken and removed the outside tube. It's really quite clever, but you need to understand how it works. So, I want you to picture an inside tube. Now here, this tube is the inside tube. That is on the inside, there. My finger is going down the inside tube. Now that inside tube is surrounded by an outer tube. this is the outer tube. The outer tube we fill with water. The outer tube is filled with water by connecting with a hose pipe. We connect that side, water goes in. Now water always goes in at the bottom end, so that when it fills up in this manner. It fills up and pushes out the air that was in there, and the water comes out this end. So water goes in there, water goes out there, and you run cold water. You run cold water through the outer tube. And when you run cold water through the outer tube with cold water will keep the inner tube, it will keep the inner tube cold. And that's the essential thing. It cools the inner tube down, and the inner tube is cooled down between there and there. So imagine steam now. Imagine steam. Or it doesn't have to be water. Imagine some other vapors, alcohol vapor, petrol vapor, whatever vapor we've got coming down there. But most of the time it's steam that we have to deal with. So imagine steam going down there. When it hits there, it's cold. Cold water from a tap. It's about 20 degrees. So 20 degrees, some of the steam will turn into drops. It will condense from steam into liquid water. And the steam that makes it past that point, this is cold. This is cold. This is cold. As steam goes down there, you can actually see it. When you use the apparatus, you can actually see the steam condensing back into droplets of water. And then the droplets of water come out the end there. Now, if you pass steam down it and some steam comes out the end, then that's not efficient. You haven't got the flow of water right. You need to turn up the tap. Water in needs to be increased. But even with a small trickle of water going through that apparatus, that's normally enough to stop any steam from coming out the end, to convert all of the steam back into droplets of water, and the water comes out the end. So cold water condenses the vapors, and it condenses the vapors by cooling them. Now, it's crucial you understand that apparatus, the condenser, the Liebig condenser. Understand it because we need it. We're going to use it in the apparatus I'm going to show you next. This is simple distillation. So let's get this sorted. Solutions. If you want solute, the dissolved stuff, if you want solute, use crystallization. Solutions. If you want solvent, if you want the stuff that's done the dissolving, like water usually, then use simple distillation. Learn that. Simple distillation is used where you want the solvent in a solution. Here, this is the apparatus. So this here is the Liebig condenser, or the condenser. You put your solution here, like salty water. You put that in there and you heat it with a Bunsen burner. The Bunsen burner heating it boils the water. The water goes up and it hits the thermometer, and you can check its water by looking at the temperature of 100 degrees. You know then it's steam. If it was alcohol, you'd know the temperature would be 78 degrees. So from the temperature that you record on the thermometer, you can follow what's going through, and what's going through hopefully will be water, and the water going through as steam. So from here, water turns to steam. The steam hits the T-junction and then is forced to go down the Liebig condenser. As it goes down, can you see cold water going in? The blue is the cold water coming out. As the steam goes through, the condenser condenses the steam back into droplets of water. The droplets of water come out the end there. There's an adapter to kind of funnel the water from the end of the condenser into the conical flasks that you've got there. So you collect pure water, and that water collected by using simple distillation, believe it or not, that water is called distilled water. Now in chemistry, in all our laboratories, we use distilled water. Distilled water is the purest of waters that we have access to in school laboratories. So we call it distilled water. In schools, we tend to have it in wash bottles with squirty spouts. We press the wash bottles, it squirts water. That is distilled water. It's the purest form of water. One of our teachers used to nick our distilled water because he used to put it into an iron. The irons would then not clog up. Quite often irons clog up because you're heating water, and the dissolved things in water, the white specks of solid you get, are the dissolved things that are in water. Well, what's dissolved in this distilled water? Hardly anything. This is the purest form of water that we have. So, simple distillation. That's how we use it. And although I've been whittering on about water from salty water, you could have used this method to separate some other solvent. Say you had sodium hydroxide dissolved in alcohol and you wanted the alcohol. You could use this. The alcohol would boil off, the temperature would be 78 degrees, the condenser would cool the alcohol vapors down, alcohol droplets would come out the end, and it would be called distilled alcohol. And indeed, the drinks industry uses this technique to make alcoholic drinks that are really of a very high alcoholic content. Except in the drinks industry, they call this a still. They don't bother calling it simple distillation. They call it a still. We use a still. What they mean is they use a still in their language to do simple distillation. Anyway, so to recap, simple distillation is when you want the solvent inside a solution. You use this. If you want the solute, take you back, use crystallization. Okay, right. 2 more techniques. Maybe I'm going to stop the video there because it's 22 minutes. I don't want to make the videos too long. I'll stop there, and next time I'm going to do fractional distillation and chromatography. Stop there. Stop.